Okay, complexity is very hard. It's really hard. It's much harder than entanglement. But my own opinion is that it's every bit as important to quantum gravity and black holes. So we'd like to find an easier way to visualize it. One hope was to follow Michael Nielsen's idea of a complexity geometry, take the space of states or the space of unitary operators or whatever it is we're interested in, and give it some sort of non-standard metric. Non-standard metric which represents the difficulty of going from one point to another by acting with some restricted class of operations. This, in mathematical terms, means a right invariant metric. For example, on the space SU2 to the n, which is the space of not the space of unitary operators of n qubits, equipped with some appropriate penalty factors for moving in hard directions. But as you might expect, the geometry that you get in this way is also extremely difficult and hard to understand. Incidentally, if it were easy to understand, we would use it and solve all complexity problems. Well, we're not going to solve all complexity problems, and so the geometry itself is very hard to think about. In lieu of that, what we would like to do is to find some very simplified model. Simplified model that makes it easy to analyze, but still captures the basic things that we think complexity should do. I won't justify it in this talk, but there is a simplified toy version of complexity geometry, and it's nothing but the hyperbolic plane, the hyperbolic disk, where the center of the disk represents the unit operator, and points away from the disk represent unitary operators of larger complexity. The further away you go from the center of the disk, the more complex the operator is. There are two ways to think about the relative complexity, ours, relative complexity. If I have two unitary operators, I can ask how many gates does it take to go from one to the other by operating, let's say, by left multiplication. And that minimal number of gates to go from one to the other is called the relative complexity. And you can think of it in two ways. You can think of it 2 points on the hyperbolic plane or on the complexity geometry. The way Nielsen thought about it was as the geodesic distance between the points, the relative complexity. The way I like to think about it, which is completely equivalent, is to imagine a non-relativistic particle moving on the geometry and think about the minimal action for the particle to go from one point to another. They are completely consistent with each other. The action point of view suggests something which turns out to be true. It suggests that if you're thinking about an ensemble of theories, like in SYK, you can start out with a whole bunch of points at the origin to follow the complexity and let them flow away by the natural dynamics induced by the metric of the space. Let them flow away, and the complexity just turns out to be the entropy of that cloud of particles. As the cloud of particles expands, the entropy grows, and the entropy, or the average, and the entropy grows, and that entropy is in fact the average complexity of the points that the cloud is covering. So that turned out to be a somewhat easy way to think about complexity, and I will use it. One of the outcomes of this view is that there's a second law of complexity. The second law just means, very simply, that there's a kind of pressure on systems or a kind of force on systems to push them toward larger complexity. In the same way, or a similar way to the way there's a force that pushes systems to larger entropy. What I'm going to tell you today is that that force is nothing but ordinary gravity.